Today we will discuss about the Vortex setting. Certain structural members are considered potentially vulnerable to fluid flow effects. Here let's have some group discussion kind of thing, like with the minutes of meeting between the engineers. Hey team, I wanted to talk about vortex induced oscillations. That's VIOS. Actually, this VIO is critical for our design, especially for structures exposed to fluid flow. Fluid flow means any kind of, like, even the wind also, it's a fluid kind of flow. Like when the wind passes through, when flows around a circular cylinder, the flow can create vortices that can cause structure to vibrate. If VI was not taken care properly, and it can lead to significant issues if you are not careful. At a low Reynolds number, the flow around these structures is symmetrical, and the Reynolds number is defined as RE equal to U D then rho. U is the flow velocity. Flow velocity means, maybe we can say that's the wind velocity, suppose if it's wind. D is the diameter of the cylinder, and rho is the fluid kinematic viscosity. Exactly, as the flow speed increases, it can become unstable, leading to vortex setting. So if the flow speed, if it is very high speed, the speed increases, there is a possibility that vortex setting, it can lead to vortex setting. This is where the Strouhal number comes into play. It's defined as ST equal to FSD ST D divided by U. U is the ambient flow velocity, D is the diameter of the cylinder, FSD is the vortex setting frequency. That's an important point. For a cylinder, Strouhal number is generally around 0.2. If the vortex setting frequency FST approaches the natural frequency of the structure, that's FN, it can cause dangerous vibrations. We should ensure that FST approximately equal to FN. So how can we prevent these issues? It should not be very close to natural frequency. The setting frequency should not be, vortex setting frequency should not approach to the natural frequency. So how can we prevent these issues? Are there any specific strategies we should consider? Are there any specific strategies we should consider? How can we prevent these issues? One way is to adjust the geometry of the structure. One way, by adjusting the geometry of the structure, we can adjust the natural frequency also, right? The geometric ratio L by D plays an important role in the VIO response. If we increase the L length of member, we can reduce the impact of vortex setting. Good call. We should also consider the mass ratio m star equal to m by half of pi 1 by 4 pi rho d squared, where m is the mass per unit length, rho is the fluid density. A higher mass ratio can help stabilize the structure, whatever the flow conditions. If we know the turbulence levels or flow profile, we can better predict how the structure will behave. The turbulence intensity is another factor we should consider. Turbulent intensity, that means where sigma u is the standard deviation of the flow velocity. Yes, understanding flow profile is essential. If it's a steady, setting might be more predictable, but if it becomes turbulent, it can be chaotic. We should also keep an eye on the Reynolds number range for different setting types. For example, periodic setting means if the Reynolds number is low, or like number is very less, then it becomes like periodic setting. If it is very high, it becomes quasi-periodic setting. Wide band random setting, narrow band random setting. This all depends on the Reynolds number. It sounds like we need a comprehensive approach, considering the geometry, mass, fluid flow conditions, and damping ratio. We should run simulations to analyze how our designs perform under different scenarios. So we should run simulations to understand or to analyze how our designs perform under different scenarios. So agreed, let's set up the plan to analyze these factors in our next project. This will help us create a safer and more reliable structures. Great idea. I'm on board. Let's share our findings with the team as we progress. Here, let's see one more thing. Like, hi everyone. Today I want to dive deeper into vortex setting observations VIOs, especially how they affect our structural design. With structures exposed to fluid flow, understanding VIO is critical preventing potential failures. VAOs occur when the flow around a structure like a circular cylinder leads to oscillations due to vortex setting. At low Reynolds number, flow tends to be symmetrical. This we have seen ud by rho is if the Reynolds number is low, the flow behaves predictably. But as we increase the flow velocity, we can see unsteady flow patterns develop. So if its Reynolds number is going up, it can cause like unsteady flow patterns. It can be characterized. We can see that. This leads to vortex setting where alternating vortices are formed behind the cylinder. Right, that's where the Strouhal number becomes relevant. It relates setting frequency to flow conditions. So what are the flow conditions? Flow velocity and the setting frequency it's relating. So it's crucial that FST approaches the FN, it can lead to resonance. This relationship can be expressed FST. Where these frequencies align, we can experience amplified oscillations that may cause structural failure. How can we design the structures to mitigate this risk? Adjusting the geometry is one option. So we can adjust the geometry and we can mitigate these issues. For example, increasing the length to diameter ratio can help dampen the oscillations. So if we increase the L by D ratio, it can increase the damping. It can help dampen the oscillations. Definitely at higher L by D ratio typically means that the structure is less affected by vortex setting. Additionally, using the shapes that disrupt the flow like streamlined designs can help minimize vortex formation. We also need to consider the damping ratio, which compares the actual damping to critical damping, can significantly influence how the structure responds to vibrations. So here we can see what type of structural members are considered vulnerable to fluid flow effects. Means certain structural members such as circular cylinder or bluff bodies are considered potentially vulnerable. What classic problem in fluid mechanics involves flow around cylinders? Means the flow around the cylinders or a bluff body. How do streamlines behave at very low Reynolds number? Streamlines becomes symmetrical, right? What theory supports symmetry of streamlines at low Reynolds number? Potential theory. Who is Strouhal number named after? Who is the Strouhal number named after? Means the Strouhal number is named after a scientist, Vincent Strouhal. What does the Strouhal number relate? It relates the vortex setting frequency. It relates the frequency of vortex setting and flow velocity and characteristic dimensions of the body. That is, flow velocity is U, characteristic dimension is the D, and vortex setting frequency is FST. In the context of cylinder, which characteristic dimensions typically used? Means diameter. How is the Strouhal number defined mathematically? Means ST equal to Fs D by U. What does the Fs represent in the Strouhal number equation? Means Fs is the vortex setting frequency when the body is at rest. D. What does the D represent the Strouhal number equation? Means D is the diameter of the circular cylinder. What does the U represent in the Strouhal number? Means that is the ambient flow velocity. What is the typical value of Strouhal number for cylinder? Means it's 0.2. And what can occur if the vortex setting frequency approaches the natural frequency of a structure? Means it can lead to significant issues like damaging vibrations. What types of fluid flow can induce alternating or unsteady patterns around the symmetrical structure? Wind, currents, and any fluid can induce unsteady patterns. Any fluid flow can induce unsteady patterns. What are the vortex induced oscillations? VAOs oscillations of cylinder members perpendicular to their longitudinal axis is due to vortex setting. Why should VAOs be studied? Means they can cause structural damage and instability. What is the range for periodic setting? Means if it's a less number in terms of Reynolds number 1022 or 0.6 in 10 power 6. What geometric ratio is important in VAO analysis? What geometric ratio? Means L by D, the geometric ratio. What does the damping ratio represent? It is the ratio between the damping and critical damping. How is mass defined? How is Reynolds number defined? U, D, rho. What is reduced velocity? Reduced velocity V are equal to U, Fn, natural frequency, divided by diameter. What is the L? Length, the diameter, mass, density. Why is this understanding of what is an important engineering? It helps predict and mitigate the potential structural failures due to vibrations. Here we can see the Strouhal number named after scientist winds and Strouhal connects the frequency of vortex setting and to the flow velocity and characteristic dimensions of the body, typically diameter of the cylinder. It defined as the ST equal to F U Fst into d by U. Fs is vortex setting frequency or Strouhal frequency when the body is at rest. D is the diameter of the cylinder. U is the flow velocity, ambient flow velocity. The Strouhal number for a cylinder remains to be approximately 0.2 across the broad range of flow vortices. If the vortex setting frequency approaches the natural frequency, then it can lead to significant damaging vibrations. In general, wind currents or any fluid flow past a structural component can induce unsteady flow patterns due to vortex setting, resulting in oscillations of cylinder members perpendicular to their longitudinal axis. So these vortex inclination vibrations are be carefully studied.